Today I want to take a bit of time, well, not only to talk about digital twins and virtual commissioning, but to spend most of the time within our software and just a little more hands-on than we have in the past. So you may have joined us for a past webinar, but if not, I'll just give you a quick primer on digital twins and virtual commissioning. And a lot of the motivation comes from the increasing cost of design changes as you move down a development cycle. If you were to catch some sort of design change that you need to make, if you're early in the concept stage or when you're doing some sort of detailed design, it's often just a matter of analyzing where that issue comes from and then working it out within software. As you move through to your prototype, even into production, the costs just skyrocket, especially if you're out in the market somewhere. This could shut down a whole line. This could issue a recall, whatever industry that you're in. So finding issues without digital twin-based techniques, that often means that you don't necessarily have as clear an idea as you could about where these issues are going to present themselves once you bring all your systems together and actually prototype the thing. So often, without those techniques, you're going to find issues a bit later on, and they're going to cost more. Where earlier, if you had some sort of digital twin, which is essentially like a system level model of how your entire machine is going to work once it's in operation. If you find issues using a digital twin, that's often in the upfront design work. So there's a little more upfront work you need to do, but the issues themselves, they're likely going to get caught earlier. Not all of them, but a lot more. So much so that some research has shown that if you just put a little bit more money and resources up front to do some work with concept level design, this can actually reduce cost overruns substantially. For some industries, that even means finding one issue that you would have found later could end up saving you a ton of money. Moving into the cost that can come in with commissioning. The process of machine commissioning, when you're trying to take that physical prototype and sync it up with the control code that you've been developing to see if these things actually work together and if they're going to perform on the shop floor as you need them. That's often a really big moment of truth for a lot of folks, and there's a lot of little issues and bugs that'll rear their head, whether it be with the prototype itself or just with the control code and its level of fidelity and real match to the machine that you're designing. And the costs there then, they're going to end up being the need to rework the code or the machine. There's just costs maybe if you want to over-engineer your machine because you don't know exactly the loads that are going to be required to I guess the torques coming out of all the different motors involved. You don't want to burn those motors out, so you'll triple the size, and that's could be an unnecessary cost. As you go further down, of course you want to keep your reputation in check. You don't want these things to fail. And overall, that means the whole process of getting to market is just a little less predictable, and that's something that ultimately does a disservice to your customers. So just to briefly outline the steps of virtual commissioning, and we'll get into some of these in product in just a few minutes. But let's say for a lot of folks, they're going to start with some sort of CAD representation of a machine that they're making. And then a typical workflow would be to take your CAD that you've done in some sort of AutoCAD program. You'll take that over and you'll bring it into our software, MapleSim. So you can import your CAD, and MapleSim will automatically break that into the different assemblies and assign moments of inertia, and will treat them as rigid bodies. MapleSim is where you bring your CAD to life in a physics-based way that is accurate and that has meaningful things to tell you about how all the systems are at play. This is where you assign the nature of the joints between your assemblies, and you drive them with motors that they're going to be correlates to the motors that you're going to actually use in your design. So you bring it to life in MapleSim, you get it ready to simulate. And then once you've got that set up, using an increasingly popular standard, it's called a FMI, or Functional Mockup Interface. This is where you can actually use some popular automation software, say B&R Automation Studio, some Rockwell software, and you can use our model as a really accurate test bed to test your control programs against. So instead of having to wait to test the accurate model in a physical prototype stage, you can do that now in a virtual stage. Mainly the benefits there being you can fix things faster. You can simulate this thing thousands of times and not have to wait for the actual machine to move around thousands of times. And it's a lot cheaper because, again, it's all in software at this point, so you don't have a lot of issues with having to machine out new parts. Going from there, these digital twins, these models, they continue to have value a bit further down the line when things are actually in production. So we're getting a little bit outside of the scope of virtual commissioning, but having a sort of gold standard of how your machine ought to perform means you can run that thing in parallel the whole time. And as soon as your machine starts to drift from its ideal performance, you're going to notice that far sooner than just what your own ability to kind of gauge performance of that machine looks like. So it's a great tool for maintenance diagnostics. And if you want to get involved in some of this, but you've already got your machines on the floor, you can sort of start from already having your machine and then continue to move in this cycle that you see here to get a digital twin out of a pre-existing machine. And that can just help you with retuning controllers if a machine's aging. There's really a lot of value in having a digital twin synced up with one of your machines. So you can kind of step in at a couple different spots in this cycle here. So chat about a digital twin already just a little bit. It's that system level model, and it has a lot to say about how you're going to be able to design a better machine up front. Whether you're more in the sort of risk mitigation side of things and you just want to iron out some issues, it's great for that. Or maybe you're trying to push your designs to be more innovative and to scale down the cost of the different components you use. It's also great for that. So it does that. It moves on to virtual commissioning. And like I said, it overall, you can plug it into many parts of your design process. And even if you just plugged it into one part, even if you just used it for a little bit better, processes and conceptual development, it can have a lot of value to be had there. So we talked already a little bit about this in the loop, but just to kind of summarize it, you move from a concept, that is often where the digital twin comes from, and you can develop that fast when you have a digital twin. Your control development, again, will happen faster and it'll be more accurate. You can also take your control program, you can put onto a hardware a physical PLC, and then you can test that physical PLC against the digital twin too. So at that point, you've just reduced so many different opportunities for failure when you bring it all together. And then you've got the rest of your benefits. This sort of lays out all the different ways that a digital twin plugs in for you and all the ways that the virtual commissioning process lets you get your hardware out faster, get it out cheaper, and with less issues. So before we hop into MapleSim, we've recently released MapleSim 2018, and one of the things that we focused on was making this process of virtual commissioning even easier and even faster. Because for how much value that this can offer and our software can offer in this world, now we know that for a lot of folks, maybe that term is new for them. Maybe virtual commissioning is something they've heard about, but they haven't really gotten close with. Or even maybe just the whole notion of system level modeling and digital twins. That could be new for folks too. So we wanted to make these processes even easier so that if you're in that space of having heard about these things but not knowing how to get started, it's easier than ever. So that's what Maple 2018 is about. We've got a new 1D motion generation app, and what that means is you can really quickly define signals now for your machine and your controllers that adhere to the velocity, acceleration, and jerk constraints of your design. So it's really a way to get your motion figured out for a machine much better. We also now support all the latest CAD formats, so almost regardless of what CAD software you're working with, you can just import that into MapleSim to get started on your model. And that makes things easy. It makes it a lot quicker than before to support all these new formats. And again, improved FMI import. So like every standard, it's always upgrading. For FMI, this means There's this FMI 2.0 fixed step co-simulation, and this is really important for virtual commissioning and running your model in tandem with control code on different platforms. So you'll have less bumps along the way. If you've got any amount of sort of CAD ready to go to plug in here, you'll find this process is a lot easier now. And that's it. With that, we'll swap out of this presentation here, and we'll hop into MapleSim. Now we're in MapleSim. So what you're seeing here, I've already got a model pre-populated. It may look familiar from a couple of these slides that I was showing you with that 3D motor. So if you can see here, there's a couple different components here. These are created as they're sort of subsystems. We could drill down into them. But what we had done to initially create this in our workspace here in MapleSim was we had gone and we had imported some CAD. And if you look here, we've got all these different CAD files supported. So we had imported, I'm just going to cancel that now. We had imported a CAD file, and MapleSim had automatically broken it out into these different assemblies here. And of course, we had some say in it, but it broke it out. And then now that we have that in MapleSim, our job was just to make it move. And with that, we brought on some joints here, some revolute joints. This is a prismatic for what you'll see is the up-down motion. We've got a variety of some motors in here. So you can see that we're setting this up in a way that is going to be accurate to how this robot is going to move in reality. And of course, to make this thing actually aligned with whatever machine you're making, there are a variety of parameters that you're going to need to tune, and that sometimes comes from specifications from motors. Sometimes too that comes from all these different components that we have ready to go. So it's with the several hundred components we have in these component palettes, it's fairly simple to find the kinds of components you need. You can just drag them in. You can start getting to work on them right there. And you can see the different ways that you can make this really synced up with what you need. So we've got here, we define like a parameter block here, which talks about, say, these cycles per minute of the machine that we're making here, and the different masses and gear ratios of our gearboxes and our motors. So we do that so that when we need to run optimizations and we need to run different tests, we can easily change things in one place, and then it'll be propagated throughout the model. So enough about that. What I'm going to do now is just I'm going to click simulate, and while this is just simulating down here, you can see it's doing all sort of work. It's generating a massive set of equations for everything, and it's going to simplify that as much as possible, and then we'll integrate through that. And just like that, the simulation has taken place. And we always provide you with a 3D simulation of what it is that's actually happening. So this was more or less a more lifeless piece of CAD before. We've broken it apart and we've actuated it with motors and joints, and we hit play here and we can see some movement. And of course it's visual. It's a good way to get a quick read on is my model actually doing roughly what I think it is? And it looks like it is. But if you really want to drill down, take a note of this plot window over here. And as I press play, you can see this blue line moving across. And all the details behind this visualization you're going to see is all collected here in real high fidelity specific numbers. So we have just set this model up that it shows you the speed and torque of motor number 1 right now. So you can see motor number 1, as you can see as we move through this, there are big spikes of torque that kind of roughly align with when the speed of the motor has to accelerate and decelerate. So it's the moving from rest that ends up having a lot to say about the torque on the motor. So we have all of that, and there's all these different all these different, I guess, variables or parameters that you can click on. You can make your own plots. So it's really an endless amount of digging into every variable within this whole model. If you're really interested in a sort of a force on a certain bearing, you can drill down and you can see exactly what's happening at every point. So there's lots of depth there. But if you are looking for some more specific applications, you're looking to do something specific with your model, let's say here, there's all these different sort of apps that we've built in that are going to cover some of the most common tasks that you'd want to do. So for example, we will open up the parameter sweep app. There it is. So if we open that up, this is an app that's going to be great for sweeping across a whole a range of values for a particular parameter, and that's going to allow you to quickly get a sense of how your system's going to perform. Say if you were modifying your cycles per minute, let's say you would say, well, maybe it could be as slow as 10, but really it's a bit of a bottleneck machine. If we could get this up to 40, that would be great. So what that's going to allow you to do, if you look in here, you can see, well, these are a variety of different parameters you could sweep through. We click CPM, you can change the values you want it to sweep through. But heck, at the same time, let's just change the mass of the load. And you might know that there's a variety of different objects that your machine's going to be handling. So you need to make sure you can cover all your bases. And because of how fast our models typically simulate, these things are seconds, they're not hours, they're not days. You can choose a variety of parameters, and you can just run a parameter sweep, and then you'll get a whole bunch of different plots here that'll show you exactly what the results are. I'm not doing it in this one because I'm going to open up a different worksheet where I'll show you some of that. But this is just to say, this is an example of a quick analysis where you can really get a sense on what the sort of operating ranges are of the model that you're working with. One more I'll show you before we get into our custom worksheet is optimization. Similar in some ways to a parameter sweep, but with an optimization, you've got some sort of objective function. You know that what you want to do. Again, let's say if we were to go over here, you know that I'll click load system, and that'll actually load our model in here. But the optimization one is great for, let's say you're trying to maximize your cycles per minute. So that's most important to you. But you know that on the other side of it here, you still have some minimum and maximum ranges of, say, the load of the mass of the load that you're going to be using. So you can set up some constraints, and then over in the objective function, you can say, but I want to maximize my cycles per minute. This will really help you dial in on that. And alternatively, to do this otherwise and to do it with so much accurate physics underneath can be so computationally intensive in a lot of other software, if possible at all. So being able to do it here in essentially a few clicks of a mouse, and to be able to control for all the other important variables, this is sort of what we mean by all the concept level design value you can get out of working with a system level model. And this, while no virtual model is perfect, and that's why physical prototyping exists, to be able to hone in 2, 3, 4, 5 times as well compared to before, that's huge. So that's really important. Lastly, if you're looking to get more specific or more in depth with your model, although we come with all these sorts of apps and templates, MapleSim sits on top of Maple, which is our computational mathematics environment. And what that means is you can more or less analyze your model as broadly and as deeply as you want. So this is an example of an analysis worksheet that was created custom. It was created using Maple. And what that means is, that all the different analysis we did here, we did them to sync up specifically with the kind of application that we're looking, which is machine design. So you can bring your system level model into Maple, and then you've got a near infinite amount of options to manipulate the math at play. So I click simulate, and I'm going to grab some simulation results from this model, and I'm going to bring it under the hood in this worksheet. And then we're going to go down here and just check out the results. We'll check out how the motors are performing. We'll look at the loading on the bearings. And like I said, at the end there, we can kind of sweep around and see the operating limits of this machine. So I'll open this up here. There we go. And this is, say, a plot here of the forces on bearing 1. And we can look through all sorts of things here. So I want to know how the speed on motor 2 is looking. You can see here that we've got the simulation took about 6 seconds because we wanted to go through 2 cycles. So you can look through all this sort of stuff, but really I'm curious about the motor itself, and for that I'm curious about the speed torque curves there, and to see what kind of torques are going to be experienced as these motors change through their speeds. So what I'm going to do here is I'm looking at motor number 2, and what I'm going to do is, this is an example, but let's say you've got a spec sheet with a whole bunch of different kinds of motors. I'm going to load that in. So we've got motor A and motor B. So I'll click on motor A, I'll get that displayed. So this is the operating limits of, let's say, off-the-shelf motor A. And this would be the operating limits of off-the-shelf motor B. So we'll take B off just for a minute here because it changes our interactive plot quickly. But you can see here that motor A looks like it does mostly the job, except for the first few seconds of, well, not seconds, sorry, but in the moments where the motor needs to quickly move from rest to higher RPMs, there's this big torque spike. And that's something that it's a very quick response. It's a very transient response, and it starts to taper out quickly. But there are some moments there then that this motor is going to be operating outside of its safe range, so that the risks increase there. It might overheat. It's overall going to reduce the lifespan of that motor. And this is a kind of effect that a lot of other simpler calculation methods, if you're using spreadsheet tools and you're trying your best to calculate effective inertias, but if you're in a spreadsheet, you might have to make a lot of approximations to really get at a usable number. And it's just hard to know how valid those assumptions are sometimes. So we don't need to make those in our software, and we can be very confident that motor A is probably not going to do the job how we want. I click on motor B, and well, heck, that's probably more than enough, as you can see here, much more than enough. So maybe we continue on, we'd find some motor that's a better fit and doesn't need to be too oversized like this. That's a way to sort of check out motor performance. We move forward. We've got some graphs here to help you understand the loading of your bearings, and that's really important for estimating the lifetime of your bearings too. So all this information feeds in to give you a much better sense of the lifing of your components and the performance of those components. And as we round out just to the end here, you could export this to a CSV. You could export this to a variety of different formats. And like I said, lastly, if you're still in the development phase, you say, oh well, I want to see the mass of my load sweep around from 2 to 22 kilograms. Same thing, maybe 28 to 34 cycles per minute. You can change these as much as you would like, but very quickly you can investigate what that would look like. You can look here and look at the speed and torque curve of motor 2, and you can see it range from right here. The torque doesn't get much higher than 200 over here, but as we start to play around with these cycles per minute and the mass, things change quite a bit. So this is just a really useful way, again, to scope things out. And all of these graphs are very interactive, and you can modify them however you need. Okay, one more thing before we wrap up here, and that has to do with the FMU generation, like I said, or that functional mock-up interface. So let's say you were creating this model, and now you're looking to design, you're looking to use this to help test out and design some of your control code. This is our FMU component code generation app. You load in your subsystem. You have all these different options depending on the nature of your control design. So there's a lot of details here where if you're invested in control design, they'll make sense to you. So once you sort of set up your model in a way that will play nicely with your control design software, then it's just a matter of boom, generate an FMU archive and export that. And once you've clicked that, which I've already clicked that, it's just before the webinar, you can see that the C code comes right out for you to be able to grab and work with right away. But of course, the FMU file is also just saved locally. So my FMU file was just saved in my C drive. And with that, you can then move on to the rest of your virtual commissioning tasks. And certainly in the near future, we're excited to show you that full workflow. And so if you're, say, a BNR software user or a Rockwell software user, we'll sort of help step you through the whole thing. But right now, you're equipped with a bit of seeing how digital twins and virtual commissioning works, and seeing how MapleSim helps sort of bring that to life. And with that, to finish on, if there are any spots in that where you thought, well, that sounds great, but don't know if I have those skill sets, or this is all kind of new to me. We've got a consulting group here that really specializes in helping you ramp up right away and helping you get results, even just for a particular project. So helping you see results from something without having to just fully flesh out a whole team of skilled engineers in this. So we've got expertise and services to help you create digital twins from your CAD, help you custom build apps. Just as you saw that machine design app, we can custom build stuff like that. That'll help you answer the questions that you need. So a whole variety of services, and if it's something that you're interested in at all, highly recommend you just get in touch, and we can help identify even a small issue that we can start to get to work on with you, and really give you a sense of the power of these kind of tools.